Okay, well, welcome to week 5 of our discussion. Just to remind you, we've been having an overall framework in which we've been talking about both the neuroscience of the experience of architecture and the neuroscience of design. And today I want to look at the third component of my view of the interaction between neuroscience and architecture, namely this idea of neuromorphic architecture, brains for buildings. And it turns out that one of the greatest achievements in this area actually goes back to 2002, the work of two of my computational neuroscience colleagues in Zurich, who created an exhibition at the Swiss National Exposition in Lausanne, where they created in this building an interactive space. Here you can see it under construction, called Ada, in honor of Ada Lovelace, who was the programmer for Charles Babbage back in the 19th century when he created a computer design based on gears and such. So let's see what they came up with. The space in action looks like this, and what is important is that this is not just a space with a few displays where people can press knobs and so on, but it really is perceiving, acting an entity that is interacting with the people inside the space. It had a brain based in part on artificial neural networks, and as we'll come to see later, Ada even had emotions and in some sense wanted to play with her visitors. And the whole pattern of interaction was guided by that idea. In thinking about an organism, we have to have sensors whereby the environment is perceived. We have to have effectors whereby one can act upon the environment. And of course, a brain that links action and perception. That action-perception cycle we talked about right at the beginning. So vision, there were both fixed cameras to monitor all the visitors in the space, but also these special cameras called gazers that could be moved to focus in on a group that was currently being interacted with. There could be several such groups at a time. And also in terms of hearing, there were fixed microphones, but also there could be microphones here, directional ones, to keep track of those groups of interest. The effectors actually combined touch and action in the following sense. The floor was an array of hexagonal tiles. Here you can see the honeycomb into which the tiles were fitted, and each one had two different capabilities. On the one hand, if you stepped on it, that would be the sense of touch. Ada could sense that somebody was standing on a particular tile, but on the other hand, there were tubes inside which could create different color patterns. And so these were ways of communication and in some sense action for Ada. And in particular, you could actually see how people were moving by saying, well, if there's a pressure here immediately followed by a pressure here with no pressure on either side, that means someone is walking in this way. And this sort of fits into our general theme of multi-sensory perception, that the touch, the vision, and the hearing can all work together to keep track of the visitors and see how they're acting and interacting. So here we just reinforce the point I've made by letting us see the floor, the way in which different patterns can be set up. So as we'll say a bit more later, we could assign different colors to people and base communication on that. Or in a case like this, one could assign several nearby people the same color, and then Ada could start moving these colored patterns together. And that would be one of the ways in which she could encourage people to form a group. So, in summary, the effectors are visual, including the overall lighting and the colored lights on the floor tiles, and even light fingers, beams of light could be pointed at people or moved to get them to go back and forth. There were no robot arms. That was a little too clunky and dangerous. But also audio, as we'll see in a moment, there was a robot composer, Roboza system, which could create music appropriate to the current interactions. So here is a list of the behavior and interactions of which Ada was capable. Now remember, this is a large space, there are lots of people, so it's not that Ada, like a person, would be interacting with just one other person or a cluster of persons at a time, but could be carrying on different conversations, as it were, with different people around the room. Anyway, the base state, if you will, we'll call it sleep, is total passive, one tile color covers the whole floor. Now, with waking, this is when visitors are given their different colored floor tiles, not necessarily everybody having a different color, but in a particular area, different people having distinctive colors. And then exploring is to find visitors who are interesting. Now, what does that mean? Well, the idea would be that Ada can do things like move the colored tiles in a particular way, or move the light fingers around, and then see whether particular people are reacting. If they don't react, they're not interesting. That's the end of it. If they do react, then we can go to the next stage, for example, to, in the way I discussed with the assigning the same color and moving those patterns together, try to direct interesting visitors to a shared location. And then she has a variety of games that she can play with people for the visitors in the space. And finally, there is the issue of using that colored pattern or the light figures to gently direct people towards the exit. Because if you're going to welcome 500,000 visitors in the space of a few months, bringing them in and making them feel engaged and entertained is important, but also getting them to leave before too long is important. Perhaps some of you may recall the anecdote about P.T. Barnum, who had his Museum of Curiosities, and there was a big sign saying, "This way to the egress." And the calculation was that most people didn't know that egress meant exit, and so they would leave to see the egress, and then of course discover themselves out on the street and having to pay again if they wanted to see more. So I mentioned this very interesting innovation in their work was that Ada, the intelligent space, not only had the effectors and the sensors that we've discussed, but also in some sense had emotion. And I should just advertise the fact that Jean-Marc Falus and I published a book back in 2005 called Who Needs Emotions? The Brain Meets the Robot. And there we had a discussion of where we were in, where we, the community, were in the exploration of biological underpinnings of emotion, but also where the robot community and the AI community was in coming up with some organizing structures that had features of emotion, and to try to encourage the dialogue between the AI and the brain community. And we asked Rodney Douglas, one of the two instigators of the Ada project, whether he would consider writing an article on do spaces need emotions, but unfortunately he was too busy for that. But the point is that just like you have emotions where you might enter a situation feeling a certain way, and then depending on how people react or whether your attempts are successful or thwarted at physical interaction, then your emotions may change. So Ada is continually evaluating the results of her actions, expresses emotional states accordingly, and tries to regulate the distribution of and flow of visitors. So here's this, we're using this terminology that we would apply to a human, and perhaps with a little more trepidation to an animal, but these guide the idea to say, can I look at the biological phenomena, can I learn from it, and can that prompt me to come up with certain control structures for a building, for a public space in this case. So Ada wants, in some sense, to interact with people. When people participate, she is happy. When they do not, she is frustrated. And also they have this idea of using the soundscape, this robot composition of music, to provide both the soundscape complemented by the visual environment of the tools and of both the ambient lighting and the tiles to get this closed loop between environment and visitor. Now, rather than go into a detailed exposition of both the emotional system and the music system, let me just refer you to this paper by Wasserman Eng. Paul Verschoor, as I said, was the co-director, as it were, of the ADA project. Donatas Manzoli is a composer very interested in electronic music from Brazil, from the University of Campinas, and they have a paper called Live Soundscape Composition based on synthetic emotions. That's the place to turn for those of you who want to see more detail. But for now, let's just look at this idea was that three things could be measured: survival, recognition, and interaction. So part of the design of the system was to instrument it so one could calculate these three values for ADA. But of course, survival for a space like ADA is very different from survival for an animal. So let's just quickly look at how these three things were characterized. So survival is, in this case, maintaining a flow of visitors. Now notice, in terms of our earlier discussion, mere survival by itself would not be a good criterion if all ADA did was encourage people to move through as quickly as possible. You could replace all her sophisticated sensors, effectors, and computations by a chute, such that when people stepped through the door, they would suddenly whiz through and be out the exit immediately. So the point is that survival has to be balanced with two other criteria, in this case recognition, and we talked before about this idea of interesting people. How successful is ADA in recognizing interesting people? And then the interaction, given that she's recognized those interesting people, how well can she get them into the interactions, those games and so on, before they are gently persuaded to go to the exit. And so this larger picture here, which is not going to be discussed, but it's just showing how her happiness is related to these three measures. And they even come up with notions of joy, sadness, anger, and surprise. And the point about those is that whether or not you would agree with the way they defined those in the computations of ADA, the point is these provide four measures which can then be used by Roboza to create that soundscape. So here we are, 16 years later, and I would say that ADA remains the high point of what I want to talk about today. But a lot of different things have happened, as we'll see as we go through the talk today, which suggests that, in fact, this idea of what I call neuromorphic architecture will go forward. So the general idea is let's design rooms, buildings, and buildings integrated into a landscape by seeing to what extent modeling the brain suggests ideas about constructing those buildings. And I'm going to use this jargon term, interaction infrastructure, for future buildings, because I don't want to say brains. I'm going to use brains for the animals and the people whose brains we are learning about. And then I want to see, can we transfer the lessons from there to think about how buildings might have interactions with the people within them or around them, based on the lessons of neuroscience. So let's just immediately observe that there has been a huge expansion in what we might call smart architecture. And so in some sense, neuromorphic architecture is the special case of smart architecture, in which the architects, the engineers working on the building or the room are informed by lessons from neuroscience. All right, so the general idea of smart architecture is the building has operative elements, so that it's not just a static entity, and they can in some sense adapt to even anticipate human activities. So walls, floors, lighting, and so on could have the ability to communicate with the user. Now we're getting more into the the territory that concerns us. So we have, in some sense, a large system to analyze in which we're not simply looking at is the heating working, is the air conditioning working, is water coming through the pipes, but we're also looking at the pattern of interaction of these, if you will, subsystems, the subsystem of the building itself and the subsystem constituted by the people within it. Then complementing the sort of thing we're concerned about is how building materials and the shape of buildings can change. And then there's the general observation outside the scope of our discussion today of looking ahead to where a building information modeling system is not just keeping track of the nuts and bolts, etc., of the building, but is also keeping track of how successfully it's interacting with people, how well the people are appreciating it, and coming up with lessons about how the building itself might change, but also lessons that can be fed back into general practice. Now, I just want to make a little sidebar here. Some architects, when they hear about the interaction of neuroscience and architecture, think that somehow this is going to reduce them to algorithms, so that design will just say, here's an algorithm, plug it in. I think it's very clear that if we look at the recent successes in artificial intelligence, such as web search and so on, we see rather the issue is not so much how do we restrict possibility and say this is the way you must do it, but rather how do we begin to navigate a huge space of possibilities that in the past we would not have known about, and what is more, maybe have access to tools to actually employ those possibilities in a cost-effective way. Okay. So let's just look at a couple of aspects that feed into this idea of a general framework in which the quest to understand the brain comes in as a possible subset. So there's this idea of ambient intelligence in smart environments. It's just what it says. To what extent can one take artificial intelligence, distribute it through an environment, and get things? So the Internet of Things that we've heard a lot about recently is part of that activity. And the cover of the Journal of Ambient Intelligence in Smart Environments illustrates this, where we've got people around the world, machines of different kinds, all connected together in various networks. So I think already you've got a feeling for how Ada exemplified that, where part of the ambient intelligence was in fact based on the study of human emotion and brain mechanisms for emotion. Others were based on using artificial networks, for example, to track people as they moved across the floor. As I sort of implied, most of this is applying ideas in artificial intelligence. Very little of it is neuromorphic, but a few of the articles do indeed mention the brain, and that's where I would hope we would see more activity in future. Nonetheless, I think one must honestly, in the next few years, face the question of will neuroscience still matter? A little while ago, we had a lead article in the New York Times Magazine on this deep learning, where a particularly simple type of artificial neural net has been tweaked so that now, when coupled with supercomputers that allow bigger versions of this neural net architecture, architecture as the shape of the neural net, not architecture of buildings, can take much larger sets of these, can run them over humongous sets of data, and adapting the connections, the synapses in the network, to get useful results. And then we've got these invasion of the home with these electronic assistants that are connected to the internet and connected to those large databases that deep learning AI is tuning and can use increasingly effectively speech communication and so on. And then here's an advertisement for Nest, where we have a controller which is monitoring so many of the appliances of the home. In other words, the current commercial realization of the Internet of Things for household products. So I would say it's clear that smart architecture with artificial intelligence indirectly affected by the study of the brain, as in the study of learning in real brains, was the historical basis for current design of artificial networks that can learn. Will it just be the case that we have that indirect relationship, or will it be, as I would hopefully claim, that there are lessons to be learned from brain-body environment interactions in diverse animals? Having said that, then, let's proceed with thinking about what neuromorphic architecture might be if the people working on developing the designs of the rooms were in fact going back to understanding of the brain. Now what's the big distinction here? Well, I think I want to go from computational modeling of brains and bodies of animals to this interactive infrastructure, this brain homologue as part of a building. And this pair of pictures is what really makes the distinction clear. So an animal is in an environment, an external environment. It's moving around, and as it moves, it's in that action perception cycle that we've emphasized in earlier weeks. And so its brain is taking information from the world, sampling information from the world, using it to direct the body in such a way that it can both gain access to new information in the world and carry out its own behaviors in the world. And then the suggestion is that for a building we have the reverse, where the world is inside the body, as it were, the building itself, and the brain is then monitoring the activity inside. Of course, this extends to the court yard outside a building, or if we worked on a larger scale, it could be the streets that link buildings and so on. But the whole point remains that nonetheless, rather than a creature that is mobile in its environment, we have a creature that is static in its environment and is mainly monitoring how the world, in particular the people, move relative to it, rather than how it moves relative to its external environment. Okay, that's the general setting, and now let me introduce some terminology that I find useful, that what I put in quotes as brain, but as I say, I prefer to call it the interaction infrastructure. Let's think about that as the neural space. So it's the sensors, the neurally inspired interaction infrastructure, the effectors, and the notion is that information flow in this neural space will support the dynamic interaction of the building with its inhabitants. And then the body, the actual building, I'll call the physical space. The standard architectural challenge for us is to combine function and aesthetics in developing this space. And then the notion is that in future, by carefully thinking about the neural space, if you like, the information flow, and the action perception cycle of the building interacting with the action perception cycle of the inhabitants, if we think more about this information flow prior to commitment to the final form of the physical space, that may yield innovative designs that can then enrich the design of the building through constraint satisfaction between its physical and neural dimensions. This term, constraint satisfaction, is an old term. As a technical term within artificial intelligence and brain modeling, it simply says that in general one doesn't pick one thing and optimize it. One has to have several different things, and the issue is, how can I make trade-offs that in the end will get me very good results for all my criteria, even though none of them perhaps has its maximal value. So, just a few thoughts about the brain before we get into details. Brains function as highly parallel adaptive computers which can adapt to changing task demands. And then, as we know, synapses, the connections between neurons, can change dynamically, and they become one of the great ways to implement learning on the basis of sensory motor and the integrative experience. But the next point I want to emphasize, which I think is a contrast between the big deep learning structures and what we can learn from the brain, is that the architecture of brains involves diverse subsystems, that the hippocampus is different from the basal ganglia, is different from the motor cortex, is different from the visual cortex, and there may be quite different cell types, or even if the cell types are the same, there may be different distributions of the cells, different patterns of connectivity. So when we have our neuroscientist hats on, we're trying to understand how it is that these different subsystems work together. But the other thing then is to think about the idea that the brain is not just a brain in a vat, it's within an organism interacting with the world in an action-perception cycle, and therefore the body may affect what the brain has to do. And in fact, let me jump ahead one, because this is such a nice illustration of the point that the star-nosed mole is a very unusual creature. So it digs its way through the earth, so it's evolved these very strong forefeet with these strong claws. But even more fascinatingly is that what is in the place that one would think of as a nose, it actually has this immense structure. So it's called the star-nosed mole because of this. But in fact, these are more like two hands in front of the nose rather than a smelling organ. And these, by a mixture of touch and chemical analysis, can detect, as the mole is digging through the earth, whether some little creature is wriggling nearby that it might want to eat. And what's interesting is that if we number the, if you like, the fingers or the rays of the star, and we go into the brain, then we find, in fact, brain regions divided into these subregions, each of which is specialized, 1, 2, 3, 4, 5, and so on, specialized to make the initial processing of the data from one of these. And then, of course, higher level processing has to figure out how to integrate that. If we can race back to Ada again, it's a little bit like having an initial neural network whose job is to process the activity from one tile of the floor to decide whether there is a significant signal there. Activity has to integrate these to find out how one might infer that somebody is actually moving in a particular direction, or several people are moving together across the tile. So in the same way, by first doing specialized computing for these receptors and then integrating them, we have an animal that can live a satisfying life, one supposes, in a way in which the brain and the body have evolved together. And so that notion of the coevolution of brain and body is what I will suggest for today as the sort of future of neuromorphic architecture, in which our understanding of the information, the interaction infrastructure, and the way in which the building goes with it can go together. Historically, one may think about the difference between crowded tenement buildings in which there is no supply of running water, no facility for the disposal of sewage, and then the revolution in urban design that comes when, in fact, each living space has to be supplied with those utilities, and then later on with electricity, and today, of course, with the internet, and that leads directly into some of our smart architecture considerations. So let's think about targets for neuromorphic architecture. Very briefly, I want to pick the one that comes closest to the sort of the things that people think about in LEED green buildings and so on, and that is homeostasis. How do you keep the building warm enough or cool enough without expending too much energy, for example? So homeostasis, when we talk about animals, is what is it in the nervous system, not necessarily in the higher levels of the cerebral cortex. Lower level circuitry can be trusted with the job of keeping critical bodily variation in the range for survival. So, for example, your brain stem can handle your breathing to maintain oxygen. It's only when you get in a desperate situation where you have to engage higher mental processes. You're suddenly in a room filling with smoke. How do you get out? You've fallen in the water. How do you struggle back to land, and so on. So homeostasis. So one example of this from quite a while ago is Nouvel's Institut du Monde Arabe in Paris, and the intriguing structure here on this wall contained all these panels, where each panel is like this, where very much emphasized by the Arabian strategy of having walls that could break the direct impact of sunshine on people behind it. But now the innovation is this is a modern structure in which all these gaps are in fact controllable, as we'll see on the next slide. So hundreds of light-sensitive diaphragms regulate the amount of light that is allowed to enter the building. So interior spaces are dramatically modified by these light patterns, and the exterior appearance is also. So we get a shifting geometric pattern with a fluid motion as light is modulated. And the next slide just gives us a close-up of one of those sub-panels, as it were, the inner ring. And what is striking here, I think, is how beautiful it is as a piece of machinery, but it's beautiful in the way in which perhaps 18th century clockwork was beautiful. And by having such elaborate mechanical work at every scale of detail, it was only a few years before more and more of these diaphragms became locked in place, and there is now a huge renovation project at the Institute, which includes the redesign of the diaphragm wall. And I confess I don't yet know what they're going to do to come up with versions of the diaphragm that are going to be much more reliable. I'd like to find that out. But anyway, what I think we have here is, if you will, the reflex level of the brain, or as I mentioned, something like the brainstem level of just keeping our breathing steady to regulate our oxygen under normal ambient conditions. Here, under normal patterns of the shift of daylight and nightfall, intense light, and so on, and keeping track just simply of the flow of light and the temperature to keep a certain homeostatic range. And to close this sub part of the lecture, what I'm saying is that our future, just as the star-nosed mole dramatically reminds us, our future is not just in terms of how do I build a brain, but it's how do I understand brain-body interactions to then transfer that into interaction infrastructure, building interactions that can then close the loop in a satisfying way for the people who are using that building. And so I just draw your attention to another source of information called Building Dynamics, Exploring Architecture of Change, edited by Branko Kolarevich and Vera Parlak, husband and wife team. And here the emphasis is on buildings that can change shape. So one of the most dramatic ones was a building that could conform itself depending on the wind passing over it, so that the wind would cause as little damage as possible and also cause as little heat loss, for example, as possible. So there was some discussion of cybernetics. This is the background really for both artificial intelligence and the mathematical modeling, computational modeling of the brain. But neuroscience really didn't come into the book at all. But again, our point is that we're not just looking at sophisticated sensors, but also the effectors. What is the way the building can change how it is performing? And in particular, here a lot of emphasis on actual reconfiguring of the shape of the building inside and outside. Okay. But I've been using this term interaction infrastructure, and the discussion of homeostasis is not really interactive. So I now want to move on to the second target, which is looking at social interaction. So we begin to have cognitive social neuroscience. I remind you, we introduced mirror neurons a little while ago, and there the idea was that there are neurons in the brain that are involved both in how we act, but also in recognizing people acting in similar ways. And so that more generally then, by recognizing how the actions of others relate to our own repertoire, we can both learn about the world and prepare for the way we will interact in different social situations. So that's, if you will, where this field is heading, still in its fairly early days. So we'd like to develop brain operating principles that support a neuromorphic architecture for what I'll call the social interaction of rooms or buildings with people in other rooms, adapting buildings to the needs of their inhabitants. And that's really where we're going to be putting our energy for the rest of today's discussion. So, speak of the devil, here's a slide to remind you about the mirror neurons. Here are the 5 people of the first paper back in 1992, Di Pellegrino, Fadiga, Fogassi, Gallesi, and Rizzolatti. And we see here a monkey brain. They were working with the macaque, and the idea is that if you insert electrodes into the brain very carefully, you can position it so you're getting the firing of an individual neuron, even though there are many, many, many millions of neurons in the monkey brain and perhaps billions of neurons in the human brain. And so what they found, recording from this area in the front of the brain, in the premotor cortex, they found, just to remind you, cells that might fire just when the monkey did a specific behavior, in this case a precision pinch, but also firing when the monkey saw the experimenter carrying out the same action. So they call these mirror neurons, active for execution of a limited set of actions and observation of a somewhat congruent set of actions, as distinct from canonical neurons that provide extra computing power for actually doing the action yourself, but that are not engaged when you're just observing somebody else's action. In other words, when you when you figure out an action, you may have to attend to specific details to guide your own muscles, and you don't have to worry about guiding your own muscles when you see somebody else, but you have to get some sort of general idea relevant to how you will learn from their behavior or interact with them. Okay. So, what I want to do in the next part is tell you about some very, very preliminary projects. I mentioned that Ada had her day in the sun in Lausanne with her 550,000 plus visitors back in 2002. Now, for many years at the University of Southern California, I had been running a course on brain theory and artificial intelligence. And the normal project I would give students for that semester would be, okay, you've learned about different parts of the brain, you've learned about how to model them, you've had some insight into how they might give you lessons for artificial intelligence, for the design of robots. What I want you to do now is go through the literature, find some papers on a piece of brain that interests you, find some modeling work, and now on that, build your own simple model of some aspect of how that part of the brain works. So that would be the normal project within computational neuroscience. But inspired by Ada, for a couple of years, I turned the project around and said, I want you to think about taking the lessons you've learned about the brains of animals and building a brain for an intelligent room. So I'm going to look at some of these. Now, a warning. These are term projects by computer scientists who are taking a lot of other courses. So they're both rather preliminary in terms of the neural space, as we called it, and they have no architectural merit in terms of the physical space. But I hope nonetheless by seeing these examples we will get some sense of the challenge of building on them to do real architecture of the neuromorphic variety. So let's do that by starting with the example of a self-cleaning room. So here the strategy was not to go, as it were, in Roomba style, where you have just a little unintelligent robot, but is one that is able to traverse the floor space of a room and do a pretty good job of covering it, given enough time. But a room that had a cleaning construct and camera system. And I think the inspiration here was graduate students thinking about graduate student housing, and perhaps roommates who were rather messy, so that it wasn't a matter of just how do I keep a nice house a little cleaner by vacuuming the floor, but rather somebody's going to spill some drink here and somebody else is going to let that pizza box fall on the floor there. So how might you detect those things? And on that basis decide which area of the rooms needs special attention. And then the system would then instruct the robot to move to the soiled areas and clean them. And as I said, let's contrast that with the Roomba that is just an unintelligent approach. So, continue our conversation about how do we make the analogy between that animal in its world and the building. I want you to think a little bit about the vacuum cleaner in this scenario. Do we think of it as an autonomous robot that communicates with the room, or perhaps we could think of it in a different way? Rather than consider it as autonomous, maybe we could consider it as just an effector. So in other words, I have this hand here, and it's, if we look at it, this is a topic we'll come back to in the next talk. It's in some sense a pretty intelligent device. It's got a lot of sensors on it. It's got, it's not actually muscles directly controlled, but tendons that can pull it into various shapes. I can feel things to guide my interactions. And yet, if I cut it off like this, which I hope we won't do, it loses its intelligence. The important point is that it is a system with a lot of onboard effectors and receptors, but it gets its fantastic capability because it is coupled into a larger system with a brain that can decide when to leave the brainstem or the spinal cord to do the necessary work versus when it needs to intervene. So let's compare a hand with the onboard touch and offboard sensors with multiple levels of processing from the relatively local blah, 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 blah. So we've got at the room level, like the cerebral cortex, you're recognizing those human actions that pose specific cleanup challenges as distinct from routine floor cleaning. And then at the effector level, as just part of the room, we've got the robot who has the onboard computation ability to both carry out the necessary cleaning in a space and figure out when it's succeeded and can be terminated. So I think this little vignette here is useful in thinking about how learning from animals and humans and brain-body interaction can enrich our discourse in thinking about the intelligent, smart architecture of the future. Now, this slide is perhaps a little overwhelming, but if you stick with me, I think I can help you make the key points that I want to get across. So, we're all familiar by now with this idea that in the hippocampus of the rat, there are cells that are place cells. In other words, what fires them most effectively is not what the rat is looking at or what the rat is doing or what the rat is remembering, so much as where the rat is in its limited environment. And we also learned a fairly sophisticated idea about population coding. If one place cell can be active over this whole region, it doesn't give us much spatial acuity. But if I've got a cell that fires here, a different cell that fires here, a different cell that fires here, a different cell that fires here, if they're all firing at the same time, then a little bit like a Venn diagram, we can focus in on a very precise area. for where we are. So populations of cells can, between them, convey information that exploits what single cells know, but can give us much more precision appropriate to our ongoing action. But let's look at this picture for a moment. This is sort of a "you are here" arrangement, right? But in general, why do you want a map, what we'll call a cognitive map? You want to get from where you are to another place. And so you need some information to get you from here to there, which means you have to represent not only where you are, but where you want to be, and then somehow consulting the map, whether it's a map on the table or a map in your head, you want to find a path that you can then turn into action. So what this diagram is saying is too much for me to go through with you now, but it's saying here's the hippocampus saying you are here, there's only one part of the action. And that in prefrontal cortex, the claim is there's what I'll call a world graph, or if you like, the cognitive map. It's the place that can say, okay, you've told me where you are, you've told me where you want to be, I have the knowledge about how different parts of the room are interconnected. And on that basis, it can decide what action to do. The consequences of that can be measured to find out whether they're satisfying or not, and then all this learning in here can juggle the activity in here that was linking the affordances and the selection of action. And the one other term I want to push here is dynamic remapping. The idea is that if I'm standing in front of what is for me the right-hand edge of a table, if I close my eyes and walk about this far, I'm pretty sure that I'm at the leftmost edge, and in fact I am. So that the dynamic remapping is the idea that I can update my estimate of where I am, both in terms of what I can see about me, but also in terms of other cues, and in particular, the cues of my own motion. I have a pretty good idea of how far I went, and on that basis I know what I'm doing. If we're driving along a familiar route, then in fact just our sense of how long it's been that we've driven may be more important than in looking at landmarks around us to decide when to get ready to turn off our current path. Now, why did I go into that? It's because this is part of the knowledge base that the students working on this project exploited. So they had various types of input, a camera, laser data, but also odometric data. This is like knowing how far you've traveled to update your place. And the path integration corresponds to the dynamic mapping idea that you can update where you are both by getting external input, but also by updating it in terms of what you think you've done recently. And then one of the things we studied at the level of our frogs is frog brains was how do you avoid obstacles. The monster picture on the previous slide was basically a navigation story, and then of course that has to go to motor control. It's not my purpose to take you throughout the whole structure here, but just to tell you, okay, the students did take what they'd learned in the course. Each student implemented part of the subsystem, and so we had a first pass on not only a neural space, but a neural space that worked. And then, of course, sadly, semester comes to an end, and the work comes to an end. But nonetheless, it's a useful example, I think, of a neural space coupled to basically a totally neutral idea of what the room is like, because all you need is cameras that can map that room and detect human motion to see where spills occur. So, second example, I apologize for the rather hideous choice of visual values for showing the nature of the room. But what's important is that this is a room to help somebody cook, where the idea is that a menu is chosen, and then the system is going to help the cook get the ingredients he needs and will help keep track of what's going on in the recipe. We'll see if something goes wrong and alert the cook and so on. Now, a colleague of mine who likes to cook, and certainly my wife, who is a beautiful cook, or chef, would not want a kitchen like this, but for many other people it might be worthwhile. So anyway, cameras are mounted on the ceiling, one on the entrance, one above the dining table, one monitoring the refrigerator and one the counter. A mechanical arm inside the refrigerator can select ingredients and place them on a conveyor belt. We could argue whether that's the best way to handle it, but never mind. The user communicates with the room via microphones on the walls, and in addition to providing the ingredients from the fridge, the system can provide, in this case, visual cues, green while the user is following the recipe, red if not, but of course we would update that to a more useful interface using spoken language to say, oh, remember you've got to pull that off the stove before it overheats, or you forgot to chop the onions, and so on. But let's look not at the rather amateurish physical space, but the point that, in fact, I could have made already when presenting the self-cleaning room is that many of the components of the room's brain are based on models of specific brain regions or guided by brain operating principles. So the idea is that we're not just saying that all we're learning from the brain is here is a way to build artificial synapses that can adapt. Here's a way to build a multi-layer structure. And now if I've got a supercomputer at my disposal and a huge body of data, I can learn useful things. But really to say, no, the brain has a lot of different regions, they do different things. Let's try to understand their specialized functions, and then maybe that will help me design the neural space for the building. And then to the extent that I use artificial network technology or more detailed brain modeling technology will be a matter of the decision as we elaborate the neural space. Anyway, here is a quick look at the neural space here. And so we have things like speech recognition, emotion recognition, event localization, processing facial expressions. Here we have totally mundane things, choosing the meal, choosing a snack, selecting ingredients. And then we have dynamic remapping, reach and grasp, of keeping track of the manual actions of the cook who's being monitored by the room, and that has to be related to keeping track of the state of preparation according to a particular recipe. So this just gives you some idea of a system design where, for example, the placement of the monitors, the placement of the microphones, the decision as to whether a robot arm is the right way to go, or simply just a reminder to get something out of the fridge, and so on, would be appropriate. Okay. So the last part of this talk, I want to briefly recall, or not for you recall, but for myself recall, a project in this class a year ago at UCSD, a project conducted by Tricia Noon, who looked at neuromorphic design of an apartment for blind residents. And again, what's interesting here is that in thinking about a blind resident, we were really working on both the issue of the neuroscience, or perhaps more generally the cognitive science of the experience of the architecture, as well as the neuromorphic design of the apartment for this person, because we're really saying, okay, close off vision, what can you achieve? So if we go back to my example of walking from A to B, okay, I can open my eyes and check, oh, I haven't quite made it yet. But if I were blind, I wouldn't be able to open my eyes, but at least I could add a tactile cue and feel my hand going along the tabletop till I reach the end of it and know I'm there. So that's the sort of trade-off between the understanding more about the neuroscience of the user versus the neuroscience of the interaction infrastructure. So in discussing this, we elaborated some of the methodology that's been implicit in our talk so far. So we're saying we have various design challenges, and here is a general set of 5 approaches linked to that challenge. They might be approached in any order. I might have to iterate and do some of them again and again. Some of them may not be necessary in a particular case, but anyway, first of course we've got to say, what do we want to do? So you might say, how does the blind person get from the front door to a room that they want to get to? And then you might up the ante by saying, okay, the visitor might want to get there, but what happens when, the resident might want to get there, but soon they know what they're doing. What do you do to help a visitor who comes? And then you have to think about, well, a blind visitor and a visitor who's sighted are different, so that you might not think about lighting. Oh, it's for a blind person, I don't need to put on lighting. But okay, if they're going to have visitors, or if maintenance people are going to arrive, or whatever, then lighting is required. Windows. Okay, if you can't look out the window, why bother? Well, they're a source perhaps of an ambient lighting that can be dimly perceived and help with circadian rhythms. There may be a source of warmth. They may be operable so that breezes can come in and out. So that what I'm showing you here is, as it were, the tip of the iceberg in trying to think through the experience of not only the person who the apartment is for, but the visitors and the tradespeople that they'll be interacting with. Okay, so define the challenge, assemble cog-neuro data and modeling, relevant as appropriate to assessing the possible experience of the inhabitant or to developing the interaction infrastructure. Offer a design that builds on these. And then, here's the interesting thing. It might be that you say, okay, I'm doing this building today, but gosh, there were some questions that arose that I would really like to know the answers to. And I think this is where the interaction between architect and neuroscientist begins to raise to a new level, where the designer can say, oh, here's something I'd like to know about the brain, or here's something I'd like to know about cognition that might help me. So here, Mr. Cognitive Science, or Ms. Neuroscientist, can you add the database of relevant material by doing some new experiment? And further, of course, the very general point is that in some cases, the specific experiment of what happens when a person is in this type of space, type of question might in fact say, well, I need more basic research. So, for example, we learned a lot about the role of the hippocampus in navigation by going to basic research on rats to be able to record individual cells, to learn about place cells, which then reconfigure the way we think about cognitive maps. So there may well be a payoff like that, although this will be, so in a way, A to C will be the normal range of activity. This will occur as the architect and the cognitive neuroscientist talk to each other, and this will be perhaps the long-term background of basic research that may be occasionally inspired by findings from here, or of course the findings may already have been made, and then it will be the task to discover their relevance up here in the application. So, as I suggested, the first problem to think about is simple navigation. A blind person must be able to navigate their living space without visual cues. So we have to give audio or tactile cues more prominence to aid the resident in wayfinding, whether or not we put in technological aids. So in her term paper, Tricia thought quite a bit about having devices that could create patterns that you could feel, which could provide little maps of the apartment. And these could have the merit that they could be attached to sensors that notice if furniture has been moved or if new obstacles have been placed, so that it will be possible to check the state of the apartment as one moved from A to B, and thus move more confidently, knowing that obstacles weren't in a familiar space rather than walking hesitantly in case there were obstacles. But before we talk about the solution, which for today I'm not going to go into that sophistication of a device of keeping an updated physical map that the blind person can sample. I just want to look at some of the data. So we might ask, well, what do we know about cognitive maps in blind people? And so here are a couple of things. I had a talk to Claudia Folska, who is herself blind, and amazingly has a TV show called Cooking in the Dark, which obviously is not intended for a blind audience, but is rather to bring to a sighted audience not only a little bit about what it's like to be blind, but rather to help them understand what the senses can contribute to the cooking experience, the senses of touch and smell and taste, that in a visually dominated culture they might ignore. This sort of fits in with the general theme of architecture, of let's not be totally dominated by the visual experience of architecture and think about the multisensory experience. Anyway, what she did for her PhD thesis was get 39 blind people who used the Colorado Center for the Blind to basically sketch how they got from the transit stop to the building. And what she found was that everyone she sampled preferred tactile to auditory cues in characterizing the way stations, as it were, on that walk from the trolley to the building. And Passini and Prue had found that the blind make more decisions in navigating complex spaces and require more information access points than those who navigate with sight. But they're still able to navigate in novel complex spaces. So what's going on here? Well, I'm standing at the moment in front of the screen in a room, and the exit is right in front of me. But in the middle is a podium. And so if, as a blind person, I were only to remember where the door is, and then my dynamic remapping would have kept pace perhaps with where I am relative to the door, then I only need that as a blind person, I would have to add the podium to my cognitive map, because then I would have to explicitly say, okay, I'm going to walk until I feel the podium, and then I'm going to use my hand perhaps to trace my way along the podium till I'm clear of it, and then I can orient myself and move towards the door. Whereas as a sighted person, I don't need to remember the podium as part of my cognitive map. I just remember where the door is relative to my current position, and I walk confidently towards it and just detour around obstacles on the way. They're not part of my map. So I think this gives us a way in which that model where I talked about the world graph as containing all these different places that one might want to go through on our way somewhere, this helps us illuminate this finding. And just to finish the point, the tactile cue is better than the auditory cue, just because if you rely on sound too much, then you might confidently go to somewhere without taking proper care about obstacles in the way. Okay, so this is just saying what I've said about the world graph and why Folska's study highlights the importance of tactile cues. And so for the design of an apartment, these cues can create familiarity and a mental map for a blind resident, creating affordances that replace the vision information. So very simply, then I'm afraid the contrast is not very good on this SketchUp representation, but this is the idea of a corridor where the floor here is crucial, not because of the color that we use to provide a visual illustration for you looking at this, but to provide different textures that could be used to let the person know where they are along along the corridor. An architect colleague, Ken Kornberg, who designs large-scale buildings for research and education, has a very nice idea, which wouldn't work, I think, in a smaller apartment. But what he has is that so that when you're in a long corridor, you can know which way you're facing if the corridor is curved instead of straight. And then you can trace your way along the inner wall or the outer wall. So that idea of having ways of curvature, but in this case tactile cues, perhaps on straight walls, to let one know whether you're traversing along the left wall going this way away from the front door, or on the right wall traversing this way going towards the front door. These could be other cues that could enter into the design. So here is the design of the environment of the apartment. And let's face it, this is a project not even for a semester, just for a quarter. And so the main issue was just to simply think through where one might want to put various types of sensors. So very discreetly, for example, there's only a motion sensor and no camera inside the bathroom. And there's a balcony out here, and so we have cameras and other sensors, but we also have devices like speakers that can communicate information. So here we're moving towards what is a relatively banal layout of the apartment to thinking through what sort of sensors might go in. There was also the idea that maybe putting furniture in ways that allow one to very confidently go from the door to places within the room without having to worry about obstacles and clutter become important. In particular, though, Tricia revisited the neuromorphic kitchen, and what I have to say is that, again, this is a one-quarter project, so we didn't get very far in thinking about the design of the kitchen, but we did leave out the robot arm. So what Tricia focused on here really was the issue of memory. The blind already rely more on memory because of loss of vision, and they need to be even more aware of where all items are and what step they're in their recipe. Because the blind cannot use visual search, they need aids to provide them with more information to help them cook. So this is the basic point, to think through the way in which you work when you're cooking if you can't rely on vision. The kitchen is a complex room, it stores many items, cooking requires a great deal of working memory, and so on. So, and keeping track, for example, if you're cutting the onions while the water is boiling, you've nonetheless got to be able to monitor in some way that the water is boiling, without, of course, relying on the tactile cue of putting your finger in it, but then maybe auditory cues become more important, and olfactory cues. Claudia Folska emphasized how important olfaction is, and she's on her TV program done things like blindfolding a chef and having them cook, and having them amazed at how subtle the olfactory cues are, that when they were combining vision as dominant sense with olfaction as a minor sense, they were not as fully aware. So, mnemonic techniques, we can go and look at stuff on the hippocampus, episodic memory, object location binding, more sequential presentation. So the suggestion was to go from these sorts of observations about the cogneuro of object memory and location to a structured organization of kitchen objects that allows the blind individual to use fairly well-established mnemonics to remember where items are. So, in terms of our organization of those 5 optional steps, we can look, for example, at here, where let's take an example of finding something, leaving the kitchen for the moment. When we look for keys, most of us can use visual search and episodic memory to find the keys. We sort of remember, well, it could be in one of these places, and that doesn't have to be a very precise location because it's easy for us to do a visual scan around those remembered areas. But a visual scan is in general much less costly than a tactile scan. So in interior design, one might have much more emphasis on designated places for different objects. You don't just put things down in the kitchen and hope you'll remember where they are. You have very specific little frames, perhaps, where you put the vinegar, where you put the sugar, and so on and so on. So, technology, one might imagine that perhaps by increasingly having radio frequency identification tags attached to objects, one could have the technology automatically identify and track the objects, and then perhaps one just asks the kitchen, where's the salt, and it will guide you in some way to where that is, perhaps by having a little specialized speaker beep in the vicinity of the object. But in terms of cognitive neuroscience, we might say, well, given the role of the hippocampus in both episodic memory, remember that patient HM who was unable to remember new episodes after a big transection that involved hippocampus, and given its role in navigation, again based on our work on the place cells, an interesting study would be to examine how blind humans integrate episodic and locomotor memory in wayfinding and locating objects. And there are some studies in which we've looked at where people do see how well people can navigate. So if you close your eyes, if you look around a space and then close your eyes, I forget the exact amount because I can't remember the relation, whether it was a old style or metric, but it's either 10 feet or 10 meters that you can walk confidently without bumping into any obstacle. And then after that, you begin to slow down and really need those haptic cues. So this idea of the back and forth between how do humans use cues, how do blind people use cues, can give us a general framework of the interaction between episodic memory, navigation, the memory of where objects are located, which is sort of halfway between a permanent cognitive map and a totally transient information. So this, as I say, is the physical space of the kitchen, and what one hopes for in the future is that here we're just simply saying, okay, here's pretty much how we would lay out the kitchen anyway. Let's make a few modifications. For example, we don't want to put storage space too high, which would be too challenging for a blind person to reach and know what they're reaching for. Let's think about where we can put in various speakers and cameras, maybe some touch sensors to check where the people are at the stove or the sink and so on. And then we can add technology, speech system that communicates with the resident, provides information, haptic tactile maps, cameras for facial recognition, and so on. And then we have a neural space that in this case is fairly similar to the previous one, except it doesn't have the robot interface keeping track of the recipes. So even if you leave the robot, maybe some of the recipe monitoring, recipe execution monitoring, ingredient reminding system that was part of the earlier design could be incorporated. But what's interesting here, of course, is that the room has visual input, even though the person does not. So at first you say, well, it's a blind person, what's visual input doing here? Remember, this is the brain, the interaction infrastructure of the room, the kitchen, not the map of what's going on in the brain of the person. But then the hope is that as we go further into our insights into social cognitive neuroscience, and as we can then think more about the human-building interaction and understand what might be in the brain of each that would optimize those interactions. So with that, I come to my last slide, the future of neuromorphic architecture. And what I've looked here is a progression from, here's the horse and carriage, and then in the early days of motor cars we had the horseless carriage, where you can see the design is minimally changed from the design with the horse. The big difference is that now, instead of having reins to control the horse, which then provides the appropriate gait to turn a corner, we now have wheels that can be controlled, can be steered to provide that turning function. And of course the motive power of the horse has been replaced by the motive power of the engine applied to those rear wheels. Now fast forward about 100 years and we have this very desirable sports car where, yes, there are still four wheels there, there's still a steering wheel, there's still a motor, but so much has changed. And so the suggestion is that I foresee a similar future for neuromorphic architecture, that as in our design of the blind person's apartment, there the design of the room was pretty much a design inspired by, oh, this is what a kitchen looks like. And in future, there may well be a very strong reconfiguration of the building space as it evolves with the constraints of the neural space and the physical space, the building space, each shaping the other to come up with a habitation or an office building or a workspace or a recreational space that is designed to be able to use some of its smarts, its brain, to be able to better enrich the experience of the people who inhabit that building. And that's it for today. Thank you.